Hello world, welcome to LeetCode Legends. Today we're going to solve climbing stairs, LC70. So it's always a great idea to start off reading the question and making sure you thoroughly understand it. So here you are climbing a staircase. It takes n steps to reach the top. Each time you can climb 1 or 2 steps. In how many distinct ways can you climb to the top? So we're looking for permutations of how can you reach the top from the floor. So here it's important to note that the order that you take steps in matters. So stepping by 1, then stepping by 2 is different than stepping by 2 and stepping in and then stepping by 1. All right, so let's start thinking about this. We can even draw a diagram to sort of help us make sense of the question. So from the floor to the third step, how many ways do we have? So we can step by 1, step by 1, step by 1. You can step by 1, step by 2. You can step by 2 and then step by 1, and that's it. And so what are we doing here? This is sort of like a brute force approach to just count how many ways there are. We're sort of backtracking, right? Like we're trying to, at every point in the staircase, we're thinking, how can I get to the end? Let me try 1 step. Let me try 2 steps and just see if either option gets you to the end. So this is sort of like backtracking. So I'm going to try to code this up because a brute force solution that works is better than an elegant solution that doesn't work, per Winston Churchill. I know up front that this is going to be an exponential time complexity solution because I have 2 choices at every point in the backtracking, but we'll take a look at it. It'll be more clear as I code this up. Okay, so we're going to need a variable to hold the final result, right? Like, is it 3 ways? Is there 5 ways? Is there 1,000 ways? So we need some variable that we're going to keep incrementing as we search for solutions. So I'm going to store this variable as an element in an array because it's easier to work with an array in Python for this. So result equals a list or array with 1 element. I'm initializing that element to 0. And I need to now call a recursive backtracking function to try out all the different possibilities. I'm going to call it solve. I'm going to pass it a few things. I'll fill this out in a bit. And I want to return this result. Right. So what does this backtracking function look like? I need to tell it what step am I starting from. So let's call it step I. And I need to tell it how far, like when do I stop stepping, right? If I happen to pass a certain point or reach a certain point, am I done? So I'm going to call that n, right? We're trying to reach the nth step. And we need the result, which I've set as a list of ints. Okay, so if we're stepping and we have stepped past the nth step, we're really in an invalid state. So if I is greater than n, don't do anything. Just return. Stop stepping. Let's go back and re-examine what we're doing. If we reach the very end, then that's a valid path, right? We've gotten to the nth step. So then we want to increment the result. So result 0 plus equal 1. But we also want to stop stepping, right? We don't want to step any further. Sorry. And so lastly, if we don't hit one of those base cases, we want to try step by 1 or step by 2 and see how that will impact the result. So solve. Let's first step by 1 and then let's step by 2. All right, so we got to fill this in. So now that I've defined that function, I know what I can pass into it. I can pass 0, so starting from the floor, stepping to n, and I want to increment the result when I find a good path. So that passed all the local test cases, and now we can try submitting it. Looks like the LeetCode gods are unhappy. Time limit exceeded, only 16 test cases passed, so it's too slow. Let's see how we can make it faster. All right, so let's try to approach this question differently. Let's look at it as subproblems, or see if we can break it into subproblems. So if I'm trying to find the result for the third staircase, can I consider previous results, like, for instance, the number of ways to reach the second step, number of ways to reach the first step? And those subproblems make sense to consider because we're stepping by 1 or 2. So can I compose the result of my current state using the results of the previous states? And if I look at this, there's only one way to get to the first step. There's 2 ways to get to the second step. It looks like I can compose the third step as an addition of the previous 2. And that turns out to be, a valid solution. So this is, recursion. So here's a recurrence relation for that recursion. Let dpi equal the number of ways to reach step I. dpi equals dpi minus 1 plus dpi minus 2. The solution to the current state is equal to the summation of the previous 2 states. Now I've used the function name dp because we will turn this into dynamic programming. It's not dynamic programming yet, it's just a function, okay? So when would this recursion terminate? We have to terminate at our base cases. We can stop when we get to the 0th step, and we know there's only one way to get there. You must be born on the floor. And we can stop when we get to the first step. There was only one way to get there. You can take 1 step. So let's take a look at the recursion tree. We have to trust that the recursion will work and give us the right answer, or we can verify it. So let's assume we're looking for the solution for the 5th staircase. Let's take a look at how the recursion plays out. Oop, we hit a base case here. Bubble back up to n equals 2. Go to the right child. Oh, we hit another base case. We pop back up. Pop up to n equals 3 again. And now hit another base case. And here we have the whole tree. So we have a lot of subproblems here, a lot of repeated work. You'll see like the function was called on n equals 0 several times, n equals 1 several times, n equals 2 several times. Even n equals 3 was called twice. So a lot of repeated work that we don't really want to be doing. So we know looking at this solution, it's not perfect, right? It's not completely optimal. But anyways, it's like a valid solution, and nothing to notice is it's not a full binary tree of n levels, right? It's, a partial tree. So it turns out this is actually more efficient than the brute force solution we did starting off, just with recursion. The time complexity, instead of 2 to the n, is now 1.618 to the n. And again, the same quote. So let's code this, right? Let's get into code for the recursive approach. Okay, so I don't need this function anymore, but I still need a helper function to implement the recursion. So let's call it dp, like I mentioned earlier. We don't need this anymore. We don't need this result variable anymore because we're not doing backtracking. And all we need to do is return our recursive function and pass it n. So the recursion will solve the problem for us. Trust the recursion. And what we said, if I equals 0 or I equals 1, return 1. That's our base case. We want to stop recursing when we hit one of those two scenarios. And otherwise, we return the result of the previous state plus the result of the previous state. Ooh, looks like it passes local test cases. We submit this solution. Again, it's faster than brute force, but is it fast enough for the LeetCode gods? Only time was up? No, it's not. So we pass some more test cases, right? That's proof that, you know, this is a little faster, but it's still not fast enough for the LeetCode gods. All right, how can we get better? So what we can do is memoize. As we're going over the tree in the previous example, we saw a lot of repeated work. So why don't we just not do that repeated work and use a technique called memoization? When you start using memoization, the approach becomes dynamic programming. This is dynamic programming. The big scary word, dynamic programming, it's just coding smart. It's saving the result of previous computations for future use. All right, so here we're going to go through the same example again, this time with a memoization table that we can use to avoid repeating work. So we start off with the recursive call to dp of n equals 5, and we recurse down the tree because we're not computing anything yet. We're just looking at our left child until we hit a base case. Fill the result of that base case in a table. So if n equals 1, the result is 1. Again, we hit a base case, n equals 0, and now we can compute the solution to dp of n equals 2 and save all of those into the table here, right? Now we will bounce back up to dp of n equals 3, and we look at that right child there. It happens to be a base case, but it's already in our table, so we don't even have to check the value of n. We put it in the table. We check what's in the table, and then we can compute dp of n equals 3, and that's 3. So if we see dp of n equals 3 again as another subproblem, we don't have to compute it again later on. So now we bounce back up the call stack, and we went to the right child of dp of n equals 4, and we see dp of n equals 2. We've already computed that. It's in our table, so we don't have to recurse any further, and we just return 2. And now we can also compute the result for n equals 4 because we have both the left child and the right child solutions. And so that is 5. And one more time, we look at the right child of dp of n equals 5. That's 2 steps back, and we have that in our table already. Don't compute it, don't recurse. And we have our answer, 8. So notice that this tree is a lot smaller than it was before. We had an exponential solution before, and now we have a linear solution. So this is time and complexity of O of n. So yeah, Genghis Khan said, elegant solutions that work are really nice, you know? So let's code this one up. So before we get into, you know, the standard way of doing it, I want to show you a quick little trick that I learned in Python 3. So when you have a recursive solution in Python 3 and you suspect that it's doing some repeated work, you can always just decorate it. So from func tools import LRU cache LRU cache none. All the test cases pass, and let's submit. So what this is actually doing is it's memoizing your function for you, invisibly. So it's not doing the repeated work, and this is actually making the LeetCode gods happy. We have now done top-down dynamic programming with memoization, and really all we have done here is provided the recursive solution. Pretty cool trick. I don't know if your interviewers will be happy with it, so let's try to do it the official way and the way that most programming languages can handle. So we need to define that memoization table that we talked about. So memo 1 for I in range plus n plus 1. So we've defined the memoization table, initialize every element to -1. It needs to be n plus 1 elements long because we need a solution for 0, and we also need a solution for n. Okay, we also have to pass in this memo table, which is a list of int. And what we're going to do here is check if the memo table has a solution or not. If it doesn't have the solution yet, we have to compute it. So if memo of I equals -1, then we compute it. Memo of I equals 1. Else memo of I equals the summation of the two previous states. Return memo of I. So we took our recursive solution and we memoized it manually without using slick Python features. And I think we can run this now. Oh, I always forget this. You gotta pass your memo table along to your recursive invocations. Okay, and now the LeetCode gods are happy with it yet again. Okay, so now let's talk about one final approach to solving this question, which doesn't rely on recursion, tabulation. So tabulation is analogous to memoization, but in the bottom-up approach. So why tabulate? Tabulation can unlock opportunities to optimize the algorithm for time and space. It removes constant time penalties like placing arguments on the call stack and retrieving return values from it. You can avoid using hash maps for the memoization table. You avoid, any possibility of stack overflow because there's no recursion at all. It's just an iterative solution. And just some people like it. Some people think better iteratively than recursively. So in the bottom-up approach, again, you need a recurrence relation. The only difference now is that we're talking about array elements instead of function returns. So let dpi equal the number of ways to reach step I. dp element I equals dp element I minus 1 plus dp element I minus 2. So let's visualize what's going on here. So now we have an array that we size very similar to the memo table. We have n plus 1 elements here. And we fill in the base cases to start off with, because we know the solution, right? For I equals 0 and I equals 1, we know that that's the base case. The solution is 1. We don't have to compute it. And we don't even often have to look back at those solutions, except for the first 2 iterations. So anyways, we start solving the subproblems in, an intelligently selected order, which is just left to right here. When we're solving the solution for the second step, we look back 2 and sum those previous states up to get 2. And we keep iterating to the next subproblem, I equals 3. The solution here is 3. We look back 2 elements in the array and add them up. 2 plus 1 is 3. We get to I equals 4, and we look back 2 elements. 3 plus 2 gives you 5. Go to the final subproblem for step 5. We look back at I equals 3 and I equals 4, sum up 3 and 5, and we get 8. So this is the bottom-up iterative approach to dynamic programming. We're not repeating any work at all, and we're just building up the solution one subproblem at a time based on the recurrence relation. Let's go this one up. Okay, so we no longer need any function, any helper function. What we do need is we still need a table. So let's call it DP, right? We said it was a DP array. And we can even leave this the same. Yep. Now we have to fill in the base cases that we talked about. So DP of 0 equals 1, DP of 1 equals 1, and we iterate for I in range 2 to n through n plus 1. DP I equals DP I minus 1 plus DP I minus 2. Return DP n, the 5th step, right? No more helper function, just pure iteration. Let's see what happens. Pass all local test cases. And the LeetCode gods are happy. Maybe happiest, right? There's no recursion, so it should be a little faster. Yeah, so this is the bottom-up approach. One thing I want you to take note of is we actually could optimize this even further for space. So because this recurrence relation only cares about 2 elements, we actually don't need to save, we don't need to continuously save these base cases. So we could optimize this to make it constant space. So this is why another reason you want to convert your solutions to bottom up or consider it is because you can optimize for time and space. So lastly, to wrap it up, just the complexity of the dynamic programming solution for this question is O of n, space complexity to O of n. You can optimize it further in the bottom-up approach. I'll leave that as an exercise to you. Thank you for joining us this week on LeetCode Legends, and it's our first tutorial here on this channel. I hope you liked the content and liked thinking about this question from multiple approaches. I think it's always great to think about what is the brute force solution of your question and how can you optimize from there. It helps you sort of understand the question more thoroughly as well. So thanks again, and signing out for this week.